The motivation of our work as follows. Contact-based robotic tasks are becoming commonplace in diverse fields such as medical robotics and assistive robotics. Versatility, contact safety, and constraint satisfaction are primary concerns. Yet, there are challenges to this work. For example, incorporating perception in planning and contact, modeling the contact interaction, data are expensive or unavailable. In this work, we explore the possibility of using the soft contact in trajectory optimization. Our setup includes a platform with a soft substrate and use the manipulator with a force sensor to perform motion and force simultaneously. On a force-controlled, low-impedance robot, force and motion are coupled since frictional forces could affect the motion and vice versa. To achieve better force and motion accuracy, we use an contact-aware optimization distributed framework. To build a contact-aware model, it is needed to derive a contact model. We use Hertz contact mechanics to approximate a valid local model. Then a dynamic model of a contact model is derived, and eventually, it is incorporated with the robot model to formulate the full dynamic model with the contact. The full dynamic model is used in a high-level planner. High-level optimization framework splits the main problem to subproblems as inverse kinematics, dynamics and contact, and constraints blocks. We use alternating direction method of multipliers, namely ADMM, to solve for each subproblem independently to find a consensus trajectory. Lower-level control is comprised of an admittance controller to mitigate instabilities, and other contact-related unmodalities. ADMM gives faster convergence, allowing us to compute trajectories in model predictive control fashion for real-time execution. The full dynamic model is used in a high-level planner. High-level optimization framework splits the main problem to subproblems as inverse kinematics, dynamics and contact, and constraints blocks. We use alternating direction method of multipliers, namely ADMM, to solve for each subproblem independently to find a consensus trajectory. Lower-level control is comprised of an admittance controller to mitigate instabilities, and other contact-related unmodalities. ADMM gives faster convergence, allowing us to compute trajectories in model predictive control fashion for real-time execution. To make it implementable in real-time, we use model predictive control by taking into account the computational and system delays. This is described in the paper. To verify the validity, we performed experiments where this video shows the most basic implementation without force control or model-based compensation. You could see it cannot maintain the contact. In this video, force control is activated. This allows it to track the force, but the motion is distorted. Also to note, initially, the force has an oscillatory reactive behavior. This is not desirable. Here, heat map shows the normalized force and motion trajectory comparison as shown. This shows the comparison of this compares the results of model-based compensation with force control alone, and the basic implementation without force control. With model-based compensation, it could be seen that motion and force tracking performance is much more accurate. These are some videos of the results. The failure cases are when you do not compensate for the friction and normal forces. Due to that, it builds up error and eventually fails. Other examples show when successful cases for the dynamic and static environments. In summary, contact-aware planning frameworks are important for safe manipulation. Local contact models are appropriate for planning purposes. Low-level interfaces improve stability and tracking of motion and force modulation. Finally, this work could be applicable in domains such as medical robotics, where contact safety is paramount. Thanks for watching.